Hello. In this video we will examine how students can use ClassWiz to support their understanding of logarithms and exponents. Turn on your ClassWiz and set it up, and we're going to start with Calculate mode in this video, so choose this with Menu and number 1. The idea of a logarithm is connected to the idea of an exponent. Let's firstly think about logarithms to base 10, which are sometimes called common logarithms. We already know that 10 to the power of 2 is 100. We describe this relationship by saying that the logarithm of 100 to the base 10 is 2. The logarithm of a number is the power to which you have to raise the base to obtain the number. But what power of 10 gives us a number that is not a whole number power of 10, such as 8? How do we find the logarithm of 8? This is a good problem for students to explore. They might look at a table of powers of 10 to see if an 8 appears. So turn the calculator to table mode with Menu and number 9, and we'll use the function 10 to the power x. And a good choice of values is to start with 0 and go through to 1, because we know that 9 is less than 10 to the power of 1, and go up in steps of 0.1. And here's our table. We'll scroll the table and look for a value of 8. And 7.9, 0.9 is close to but not the same as 8. So looks like the power has to be a little bit more than 0.9. So let's change the table values a little bit. We'll start at 0.9 and go to 1, this time in steps of 0.01. And again look at a table and see that the value of is too small there and too large there. So we could continue that process just to do it one more time. Start with 0.9 and finish with 0.91, which we know is too large, and change it to 0.01. And now we're looking for an 8, remember? Somewhere down here is an 8. 0.903 is not enough, and 0.904 is too much. So we could get closer and closer to a value that when we raised 10 to that power would be 8. Of course, there's a more efficient way of finding the logarithm to the base 10 of a number using a command, a logarithm command. We'll move back to Calculate mode with Menu and 1 and use the logarithm command. The base is 10 and the number is 8, and the ClassWiz gives the result immediately. And we can see that this is the number to which we have to raise 10 to get 8 by raising 10 to the power of the previous answer. And we can see that the result is 8. And this same sort of result is true for any number, of course, not just for 8. So if we have 10 raised to the power log to the base 10 of any number, like 23, then the result is exactly 23. Since we know that 10 to the power 0 is 1, then the log to the base 10 of 1 will be 0. On ClassWiz you can also use a different function to find logarithms to base 10 without having to enter the base of 10, which is perhaps a little bit easier. Over here on the left of the keyboard you can see the word log above the opposite key. So we could say the shift and the log are, and don't need to enter the 10, the log of 8 is exactly as we had it before. Or if you like a log of 100, what number do you need to raise 10 to get 100? It's 2. Now, logarithms were once very important for calculation purposes, as they made it easier to perform calculations like multiplication and division and powering than it was by hand. The main idea here is that when numbers that are powers of the same base are multiplied, the exponents can be added. For example, if we think of having a base of 5, 5 to the power 3 multiplied by 5 to the power 4 is a result, and I'm going to use the factor command here, shift and factor, is 5 to the power 7. So this relationship about indices, if students understand that relationship, they'll know that if they can write a number as a power of 10 using logarithms, then to multiply the numbers they need only to add the logarithms. And of course adding is a lot easier than multiplying. So in this particular case, if we were to, you could test this out for yourself, or students could test it by getting the log of 3 and add that to the log of 4, say. We add those together, we get a certain result. That's the same as the log of 12. So in practice, logarithms were used with table books instead of calculators, of course. But the idea, the basic principle, is one that relates to the use of indices, and students can see that for themselves with ClassWiz. Similar ideas for use for division, which involves subtracting logarithms. So to find 57 divided by 17, you first need to subtract the log of 57. From the log of 57, you need to subtract the log of 17. And we get a certain result when we subtract one from the other. And if we raise 10 to the power of that result, the answer, we'll get the result 57 divided by 17. So students can see how logarithms work, and they need to understand something about indices, but the ClassWiz helps them with that as well. Finding powers and roots using logarithms involved multiplying or dividing. For example, to find 5.2 to the power 6, you would need to multiply the log of 5.2 by 6. And we get a certain result. And to see what the result was, we need to raise 10 to that power. So 10 to the power of that previous answer gives us a very complicated result. And of course, these days, the calculator does that directly. So 5.2 to the power 6 gives that same result. Of course, the calculator itself is using logarithms, and students who want to understand how the calculator works need to understand how logarithms work. So the ClassWiz is being used here to see how and why logarithms work. We no longer rely on them to calculate, of course. And so far we've only used a base of 10, mostly for the historical reason that logarithms to that base have often been used. But any base is possible. The same idea connecting exponents and logarithms applies. For example, 7 to the power 3 is equal to 343. So you would expect the logarithm of 343 to the base of 7 to be 3. It's the power you must raise 7 to in order to get 343. You can see on the calculator logarithm to base 7, and I'm moving across with the cursor each time, of 343 is 3. The logarithm of 1 in all bases is 0. So let's choose logarithm to base 7 again of 1 will always be 0, because 7 to the power of 0 is 1. Other properties like the logarithm to the base 11 of a power of 11, like 11 squared, the power you have to raise 11 to get 11 squared, of course, is 2. And so that logarithm of 11 to of base 11 is 2 in that case. Similarly, if you have numbers that are less than 1, the logarithm to the base 8 of the number 1 over 64. What power do you need to raise 8 to get 1 over 64? It's 1 over 8 squared, so it's the power of -2. So as you can see, understanding logarithms and understanding exponents go hand in hand. Logarithms allow some problems to be solved directly. For example, consider the equation, what power of 2 gives you 15? The number that 2 must be raised to obtain a result of 15 is simply the logarithm of 15 to the base 2. Logarithm to the base 2 of 15. And we can see we get a big result there. And we could check this result by raising 2 to that power. 2 to the power 3.90689, and students would have had to have written this down, 0596. It's a complicated number, and 2 to that power is 15. That's how logarithms work. So finally, ClassWiz allows you to work with natural logarithms, which are important in understanding many natural continuous growth processes. These use a base of e, which is a number 2.71828. You can see this number, this symbol on the bottom row of ClassWiz, and there's a special symbol for obtaining this. So alpha, and down here you can see, use the alpha button and this key, and you can see E, and the value of E given to an approximation is shown there. The natural log of a number can be obtained with the natural log button over here. The natural log of 13 is the number that E must be raised to get 13. And we could easily check that. You notice above the natural log button there is an E to the power. So we could say E to the power, the previous answer gives us 13. So the relationship between powers and logarithms is the same for natural logarithms as for other bases. Exponential functions are widely used to describe natural growth processes using continuous change. The idea of continuous change is shown in the model here. If an initial quantity, let's call it P, grows continuously, then the amount will be P to the power E raised to the power RT after a period of time if R is the rate of growth. So let's see how that works. Sometimes investments are described as changing continuously instead of quarterly or monthly or daily. For example, if you deposit $500 into an account that's earning 4% per annum and the interest is compounded continually, then the result after 5 years is the 0.04 is the rate, and the number of years is 5. This will give us the result to which the money in the bank compounds after those 5 years, if it compounds continuously. After just 1 year, I'll go back and edit that and take out the 5 and just have 1 year. After 1 year, the $500, if it's compounded continuously, will be valued at $520.40 and a bit more. You can see it's a little bit more than 4% interest. So continuous growth is a little bit different from other kinds of growth. The exponential function is very important for modelling continuous growth and decay and natural processes. Well, that's the end of our adventures with logarithms and exponents. You'll find that Module 6 of the ClassWiz book contains more information on how ClassWiz can be used to deal with logarithms and exponents, as well as detailed explanatory text which can be copied for students as well as teachers. The module includes some exercises to check efficient ClassWiz use, some examples of activities to suggest educationally valuable things to do, and some guidance for teachers. You can download this book freely from the Casio Worldwide Education website. Happy calculating!